Here we have fluid flowing through a pipe, a 12-inch diameter pipe. Its velocity is 1.65 feet per second. And we're asked, what is the velocity if at the end of this pipe we attach a nozzle which reduces the diameter down to 3 inches? So at position 1, our diameter is 12 inches, velocity is 1.65 feet per second. And then at the end, we have this nozzle that reduces the diameter down to 3 inches, and we're asked to find what the velocity is. Now, this is a problem that is a direct application of the continuity equation. And so we're told that this fluid is, or we assume that this fluid is incompressible. We assume that there is steady state flow. And so the continuity equation applies. Mass flow rate at position 1 has to equal the mass flow rate at position 2. And so the mass flow rate is equal to rho density times the linear velocity times the cross-sectional area. And so we have rho 1 v1 a1 is equal to rho 2 v2 a2. Now, because this is incompressible, we know that the densities are going to cancel. Note that we aren't told what this fluid is. It could be water, it could be benzene, it could be whatever. It's probably water, but because the densities are constant, anything related to the properties, the chemical, physical properties of the fluid are going to cancel out, and so we really don't need to know what this fluid is anyway. But what we're left with is V1A1 is equal to V2A2, and if you remember, the volumetric flow rate is also equal to V2A2. So volumetric flow rate in this case, because it's steady and incompressible at position 1, is also equal to the volumetric flow rate at position 2. So now we can start plugging in our numbers, and the first thing that I usually do is I calculate the areas. So I calculate the cross-sectional area at position 1, I calculate the cross-sectional area at position 2, and then we can take this, we can plug this into our continuity equation and solve for V2, the velocity at position 2, and we're left with V2 is equal to V1A1 over A2, and in SI units we get a velocity of 8.05 meters per second. In American engineering, our velocity is 26.4 feet per second, and note that at position 1 it was 1.65 feet per second. That's quite a big increase in our velocity, and this is what we would have expected because a nozzle is designed to increase the velocity. And one thing I want to note, we'll talk about this later when we talk about the Bernoulli equation, but the velocity will increase at the expense of pressure. And I've seen a lot of students in the past, they tend to confuse the effects of velocity and pressure. And so it may feel like the fluid is coming out at a high, we kind of tend to think it's coming out of a nozzle at a higher pressure, but no, it's coming out at a faster velocity but a lower pressure than that fluid is upstream.